Such problems are always about how do you choose something or other to make something the maximum possible or the minimum possible. That's what optimize means, do it the best way possible. And this is a major application of calculus. And I outlined an example. This is an easy optimization problem. Last time I wrote this down, I'm just going to write it again. This is about my maple syrup business. When I make X jars of maple syrup, it says X jars, my profit is f of x is minus 6 minus x squared plus 40x. And my capabilities is I can make up to 100 jars. This is not a true story. I do make maple syrup, but I make far less than 100 jars, and I don't make any profits. It's all losses. All right? The question is, how many should I make to maximize my profit? How many should I make to maximize profit? And now this is a made-up example, but I hope you can imagine that problems like this are extremely common in the real world. People want to answer questions like this all the time in the real world. All right? And what it comes down to is basically this is a problem in which I'm trying to find the absolute maximum. We're looking for the absolute maximum of this function, f of x. And when you're looking for an absolute maximum or minimum, you require the function, and you also need a closed interval in order to guarantee that the absolute maximum exists. If you don't have a closed interval, then maybe there is no maximum. So we're looking for the absolute maximum of f of x on the interval. Typically, you have to sort of read between the lines from the words to discern what the interval of allowable x values are. And in this problem, it's in these words here. I can make up to 100 jars. So the allowable values for x, in this case, are 0 to 100. We assume, I suppose I didn't say it exactly, but you could make 0, any number from 0 up to 100. All right? Now that I've distilled this into a function here and an interval here, then we just do the usual absolute maximum thing. So as in many kinds of word problems, in these optimization problems, often the hard part is just kind of setting it up. And then by the time you set it up, you just do the absolute maximum thing. And what is that thing? The thing is you find the critical numbers, and then you just test the values. You test the value at every critical number plus at the two interval endpoints. So that's what we're going to do from now. Find the critical numbers, and then I will say plug in values. I hope you remember how to do this. At the critical numbers and the interval endpoints. Let's see if we can do it. Remember, the critical numbers are points where the derivative equals 0 or the derivative does not exist. So here's my original function. I want to take the derivative to get the critical numbers. So let's do that. This is an easy derivative to do. It should be minus 6 goes away. Then I get negative 2x plus 40, right? And this is the derivative. Critical numbers means you set this equal to 0 and solve for x. And then you also say when this does not exist. This one always exists. It has no funny business there. I'm going to set the derivative equal to 0. All right, this is meant to be an easy example. Everything's going to work out great. Minus 2x, equals 0. Minus 2x equals negative 40. Solve for x. X equals 20. All right? Okay, I'm going to plug all the values in, which are all the critical numbers, which are inside the interval. If the critical number is outside of the allowable interval, then you don't care about it. But in this case, it is inside. So we're going to plug in. Make sure you keep it straight. You have to plug into the original function f of x, not the derivative, which I just found over there. It's the original function, which is the more complicated one. I did this at a time in my calculator. I hope you don't mind. When I do f of 0, well, this one you can easily do by hand. It's minus 6 minus 0 squared plus 40 times 0. I'm plugging into the original function. I get minus 6. That means if I make no jars, my profit is negative $6. That's actually, maybe that sounds nonsensical, but this is actually fairly realistic in the sense that, maybe I have to pay $6 just to get all the equipment. And if I end up not making anything with it, then I lost money, right? I had to buy like the spikes that you stick into the tree. I think I spent more than $6 in reality. Anyway, I'm also going to plug in 100. That was the other endpoint. This I plugged in, minus 6 minus 100 squared plus 40 times 100. This, I used my calculator. I got negative 6,006. So if I make 100 jars, I lose a lot of money, I guess, because I can't sell enough of them, and I wasted a bunch of money making the maple syrup, right? My principal expense is the fuel to cook it, right? I cook it on the grill, which uses gas. Anyway, and then 20 is the critical number. This I plug in, minus 6 minus 20 squared plus 40 times 20. This is 392, all right? Having plugged in all the numbers, I'm looking for the maximum, remember? And so you just look at those answers, and you decide which one is the maximum. This apparently is the maximum, all right? I also can tell what the minimum is, but the question in this problem had nothing to do with the minimum, so I don't care about anything other than the maximum. All right, that's basically it. Now we should look back at the original question just to make sure we're answering specifically the question that was asked. The question is, how many should I make in order to maximize the profit? So what's the answer to that question? 20 jars. That's right. This number here is actually what the profit is. It means when I make 20, my profit will be 392. But to answer specifically the question, I should make 20 jars. All right? That's how we do it. Any questions about that? This was meant to be an easy one. I basically just told you everything exactly the way you wanted to hear it, and then you just find the absolute maximum. All right? So the ones we're going to do from now on are a little bit more complicated. Okay, let's try another one. How about this? This is kind of an obscure, made-up geometrical sort of example. Let's say I'm making a cardboard box with no top. And my strategy is I start with a big square of cardboard. And I'm going to say a 12-inch square, starting with a 12-inch square and then cutting out, I'll draw a picture here in a moment so you can tell what I'm talking about, cutting out the corners. So the idea is I have a big square, and before I cut it, it's 12 inches on each side. It's a square. And I'm going to make a cardboard box with no top by cutting, like here, cut out that part, and that part, and that part, and this part, right? And then you kind of fold along the dotted lines, right? And it makes a rectangular box with no top. This is the setup, all right? It's not in any way based on a true story, although you could do this if you wanted to, all right? You start with a big square. You cut out squares. I want to cut out squares from the corner, okay? And my question is, how big should I cut out the squares in the corner? How big should the cutouts be? By how big, I mean how big should this little length be on the cutouts? The length of the squares that I'm cutting out, the side length. How big should the cutouts be to maximize the volume of the box? All right, that's the question. You can try to like visualize this geometrically. I would say the answer to this question is not obvious. I mean, if you only cut out a tiny bit, then the box will be like very short, right? The part that you fold up will be very small, and so you won't get very much volume out of it. But if you cut out a huge amount, if you make these really big, then the sides of the box will be taller, but the box itself will be like narrower once you fold it up. And so again, you won't get much volume when you make these things really big. So I guess somewhere in the middle, there is a specific length here which gives you the most volume. That's what we're looking for. Right? Tell your friends, this is a real world problem. It could be. Okay, let's see if we can do it. Obviously, this has something to do with maximizing something, but it's not immediately obvious sort of how do we even begin? There's no equation for anything or anything like that. So I have, just like we did with the related rates, I have a few sort of informal steps that might help to structure our thinking about this. So here's my steps. Can I just write the steps here? And then we'll go back to this specific problem. So first of all, figure out what exactly needs to be maximized or minimized. Maximized/minimized. All right. Now in this particular problem, it's the volume of the box, right? Because I said so. I said maximize the volume of the box. In some problems, you have to read the words carefully to figure that out. Okay, and then figure out what needs to be maximized, minimized. Okay, then write a formula for this thing, the thing that's going to be maximized or minimized. Write a formula for it in terms of one variable. All right? Called, f of x. Usually it's going to be a function of some variable, x. All right? Then you want to decide the allowable interval. Remember, in these problems, there always has to be a closed interval, which usually they're not just going to tell you the interval explicitly. You have to read the words and sort of figure out what the interval should be. Anyway, decide the allowable interval of x values. And then the last step, do it. By that point, you have the equation, f of x, and you also have the interval, so you just do the absolute, either looking for the maximum or the minimum. All right? This is my very informal sort of four-step process. Okay, so let's go back to our example that we're talking about here. First question, what exactly needs to be maximized or minimized? The answer is the volume of the box. All right, so in our example, we're maximizing the volume of the box. All right, I'll redraw that picture here. It's like this, and then we have these corners that are cut out. We are trying to maximize the volume of the box, and I would like to write a formula for the volume in terms of one variable. Maybe we should think about what's the variable going to be in the first place. Any ideas? I mean, I told you already, this whole thing is 12, right? What should our variable be? You should think about what are we trying to, usually it's like you try to choose something which makes something, the volume the biggest or something like that. What is it in this case that we're trying to choose? The height of the box? Okay, yeah, can you say on this picture? Do you see that anywhere? Yeah, how about this distance right here? I'm going to call that x. That's the variable x, not the x'd out x's, right? Yeah, I'm going to make a variable there. I mean, this is the thing that I asked in the question, how big should those cuts be, right? That's the variable that I want in this problem. Okay, can we write a formula then for the volume of the box after you make it? Maybe you could draw a little diagram of the box after you fold it up. So the folded box looks like, you know, actually I don't know if it's helpful to draw this diagram. Like he said, this X actually, after you fold the box up, it's there, right? When you fold the sides up, X is the length of one of these sides here. It's also the length of one of these sides. And those, when you fold them up, the X ends up being the sort of the vertical height of the box. There's no top on the box, right? What's the volume? I would like the volume. If you want to know the volume, you also have to know this length here and also this length here, right? Because the volume of the box will be the product of those three things. On the original picture, that would be, I think, this distance and this distance, right? Can we figure out what those distances are? Like maybe the vertical one here, this one here? I think you can say what that is in terms of the variables. Remember, the cutouts are square, so this is x here. This is also x here. What do you think? What's this distance here going to be? What do you think? 12 minus 2x. Yeah, the whole side is 12, and then I'm taking away 2 of these x's to get this piece. So this piece right here is 12 minus 2x. And since everything is a square, I think that's also this distance, right? 12 minus 2x. Everything on the picture is a square, so those two distances are the same. So that's this, and that's this. And now that you know all three sides of the box, you can write down a formula for its volume, all right? This is all sort of preliminary stuff that we have to do before actually doing the absolute maximum thing, which happens at the very end. So the volume of the box then is, I'll write it as a function, maybe v of x, v for volume. It's the product of those three things. It's x times 12 minus 2x times 12 minus 2x. This is the volume of the box. And that is what I want to maximize, right? I would like, just because eventually this problem will involve taking the derivative of that, maybe we can simplify this a little bit. I'm going to just distribute everything until it looks like an ordinary polynomial. Then it will be easiest to do the derivatives. Like you could leave it as written, but it's a product of three things here. You'd have to do the product rule like twice or something. I don't want to get into that. So let's just multiply this all out. So I'll leave the x here, and then multiplying these guys, 12 times 12 is 144, and then I'm doing the FOIL, right? Minus 2 times 12 is negative 24, and then another negative 24 is minus 48x, and then on the end, plus 4x squared, right? And then I distribute the x. So it's 144x minus 48x squared plus 4x cubed. All right? I just did that because in a later step, I know I'm going to have to take the derivative, so you might as well simplify it as much as you can to make the derivative steps easier. All right, we're getting somewhere, I think. How about the allowable interval? That's the next step. All right, remember the first step was just like figure out what are you supposed to maximize, then write a formula for it in terms of one variable. That's what we just did. That's typically the hard part, is getting this formula. You have to, in this case, do a lot of simple geometry. Okay, next, the interval. Now, I didn't say anything about the interval in the original statement of this problem, but you got to look at the scenario here and just decide for yourself, based on the geometry here. Maybe I'll draw this picture again. I'll just draw maybe this much of it. Here's x, right? Here's 12. There's another x right there. Just looking at the picture there, you just think about what's the smallest the x could possibly be, and what's the biggest the x could possibly be. What do you say? What's the smallest you could imagine the x being? I would say 0. Someone gave me the signal. Yeah, I mean, this wouldn't make, this obviously would not make any volume in the box, but You could, in theory, choose x to be 0. X doesn't make any sense at all for x to be negative. So I would say the smallest possible x would be x equals 0. And how about the biggest? What do you think? Yeah. 6. Yeah, just looking at the picture here, x equals 6 would be, like, in theory, the biggest possibility for x here, right? You couldn't get any bigger than that. So x equals 6. So my interval is going to be 0 to 6, right? Where actually, I just because I can tell with the geometry, I kind of know ahead of time, the maximum volume will not be at 0 or 6, because those are both going to be 0 volumes, basically. It's going to be somewhere in between. All right? I think we're ready to actually solve the problem now. We have our formula, which is up there at the top in the box, and then we have the interval. So we do the usual absolute maximum, absolute minimum business. It's only maximum in this case. Okay, so let's, the last step is do it. This involves taking the derivative, right, to find the critical numbers. So the derivative of that thing that used to be in the box there, 144, whoa, sorry. I hope you can see it without scrolling. 144, what was next? Sorry. Minus 48x squared, I take the derivative of that, I get 96, right? Minus 96x. And then plus 4x cubed gives me plus 12x squared, right? I think I did the numbers right. This is the derivative. I need to set this equal to 0 to find the critical numbers. Maybe we can factor this. I'm going to factor out 12. And would you mind if I write it the other way around? I like writing it the other way around. 96. Anybody know their 12's? Is that 8? I think 96 is 8 times 12. And then 144 will be, well, I think I did that right. Divide out by 12. And now we can factor that, I hope. Can anybody factor that? What do you say? Yeah, minus 6 and minus 2. Yes? Okay, so the solutions then, v prime of x equals 0. My solutions are x equals 6, x equals 2, right? That 12 on the front doesn't affect anything in terms of the critical numbers. X equals 6 and x equals 2. Okay, almost done here. Now we just plug the numbers in. Use your calculator. We have some big numbers involved. Plug in. So I'm going to copy this formula just so we have it down here. Remember to, in this step, use the original function, not the derivative. I'm going to plug in v of 0 and v of 6. Those are the interval endpoints. And then also v of 2, which is the critical number. It turns out 6 is also a critical number. Whatever. It doesn't matter. You're still going to plug it in, right? Plug it in twice if you want. It doesn't matter. V of 0, that's easy enough. You get 0, right? And v of 6, also, I happen to know, you're going to get 0. You could plug this into your calculator if you want to. But just because of the geometry of the situation, if you actually let x be 6, you're going to get a 0 volume. So this is also 0. V of 2, this is the interesting one. You plug this in. 144 times 2 minus 48 times 2 squared plus 4 times 2 cubed. I used my calculator on this, and I got 128. So that right there is the maximum. And we're basically done. I think the question, so again, look back at the question to make sure you are answering specifically. The question was, how big should the cutouts be to maximize the volume of the box? And so the answer is 2, right? This distance right here should be 2 inches. That gives you the maximum volume of the box. So I will just say that cutouts with length 2 inches will maximize the volume. There you go. All right. We did it. Slightly tricky geometry there. Any questions about that? Great. All right, I got a couple more. I got 2 more to do, and then I had one for you to try. I don't know if we'll get that far today. Probably not. These can take a little while to do them all. Sorry, my paper's... Okay, this is vaguely inspired by a true story, but not really. Let's say I want to send a 2-inch high, this is again about a rectangular box. I want to send a 2-inch high box, but it's not necessarily square, it could be long or whatever, through the mail by U.S. media mail. I noticed this somewhat strange thing because I was selling stuff on eBay, and I sometimes, if you're selling a book or like CDs or something, you can send them with this special media mail, which is slower but cheaper. Anyway, the rules for how big your box can be, I found this very strange when I learned this rule. U.S. media mail, the rule is how big can the box be? The maximum combined linear distance must not exceed 108 inches. This is the rule. Where combined linear distance of a rectangular box, a rectangular box has a length and a width and a height. Let's call it this, length, width, and height. This combined linear distance means the length plus the width plus the height. I find this to be a very strange measurement. Why don't they just use the volume to tell how big the box is? You ask the person at the post office, how big is my box allowed to be? The answer is not in terms of the volume. It's in terms of this weird measurement. You add together the 3 dimensions rather than multiplying them. This seems strange to me. Why don't they use the volume? Anybody have any ideas about this? You want to theorize? I think I know the answer why they don't use the volume. They instead use this weird length, adding the lengths together. Talk about it with your friend. I think so. You want to hear my theory? My theory is, if they give you a volume like like 4 square feet, cubic feet or something. I don't even know how big that is. Any idea? Yeah, right. I think that's why. They don't want you to bring in like a 100-foot long straw or something. You'd say like, this is a tiny volume, so you have to take it. They'll say, no, it's too big. And you say, no, it's not big at all. It has a tiny volume. They say, no, big means you add together the things. They don't care about the volume. Because it won't like fit in the truck or something like that. I think the rules are similar on like for airplane luggage. They also don't measure things by volume. They measure things by this weird adding the dimensions together. Strange but true facts about the way our world works. Anyway, what I want to do for this problem, I want to send, let's say my box is 2 inches high. The question is, what's the biggest volume box I can send according to their rules? All right. The rule is not about volume, but if my box is 2 inches high, what's the biggest volume I can send? What's the biggest volume box I can send? That's the question. And then let me ask sort of as a follow-up, and which dimensions give you that biggest volume? All right. What's the biggest volume that I'm allowed? And which dimensions will give that to you? Okay? So, this is the scenario. Let's try and go through my sort of very simple steps. The first step was figure out what exactly you're trying to maximize or minimize. And again, I think it's pretty clear the way I asked the question. You're trying to maximize the volume, right? So we'll maximize the volume. All right. Next order of business, write an equation for that thing, the volume, using only one variable. This is the tricky part usually. Equation for the volume using one variable. In this problem, actually, it's the one variable bit that's a little tricky. I will draw that same picture that I drew before. It's the picture that I want to think about. Only, remember I said the height is going to be 2 inches. So this I will just write as a 2, right? The rest of the box has 2 other dimensions, and I didn't say it was going to be a square, so they are just 2 other numbers. Yeah, something like that. Would you mind if I just, for now, I'm going to call this, let's just call them, say, x and y. The issue is we have to write this using a single variable, and this is what he was trying to address. I want an expression, an equation for the volume using only one variable. So, as written, just as a first attempt, I can say the volume is 2 times x times y, right? This is a good start, but not quite good enough because the y there, because I only want one variable, right? And so what we have to do is write that y in terms of x, right? We need to express y in terms of x. And just from this picture here, there's no way to do that using only this picture. You got to look back at the question for some more information. And the more information in this case is that these things here are supposed to add up to not exceed 108. Now, if I want to make the box as big as possible in terms of its volume, I'm going to actually make it add up to 108. Like I'm going to max out this thing here. So this is the other bit of information. We'll also have these things adding up to 108. 2 plus x plus y equals 108. Huh? 108, right? That's because I'm going to make the box as big as I'm allowed, which is I'm going to have those things adding up to 108. And using that, we can indeed express y in terms of x, right? That's the purpose of this. So I'm going to solve that for y. And what did it say? Subtract 2 first, so it'll say x plus y equals 106, and then solving for y, 106 minus x. Right? Plugging that back in here will give me an equation for the volume using only one variable, x. That's what we were looking for in order to finish it off. So the volume is 2 times x times 106 minus y. Right? 106 minus x. Right? This is a formula for the volume in terms of a single variable. And like before, I'm going to distribute that just because it'll make the derivatives easier when we eventually take the derivatives. And I'll write it as a function. V of x equals, so distribute here, 212x minus 2x squared. Right. I'm feeling good about that. How are we doing? Okay, what comes next? This is the formula that I'm going to do the maximizing with. We also need the interval of allowable values. So for the interval, I will just look at sort of what's the smallest possible x and what's the biggest possible x. and make an interval out of them. What do we have to go on? You can look at the picture. Last time I sort of read this information off of the picture, but actually in this example, the picture doesn't really suggest a biggest possible value. Actually, I would say the smallest for x would be 0 in this case. It doesn't make any sense to use a negative value for x. So I'm going to say the smallest possible x is 0. It just doesn't make any sense to go less than 0. But the biggest, when I look just at this picture, the biggest is not clear, right? Anybody see, how can we tell what's the biggest possible value of x, if not from this picture? There is another thing which kind of limits how big the x could be. Yeah, I think if you got to look at this thing, right? 2 plus x plus y has to add up to 108. So based on this formula here, the biggest the x could possibly be would be 106, right? That would be if the y was 0. Then the x could be 106, but no more than that, all right? So the biggest x is 106. Basically, you're looking at x plus y equals 106. That's that equation from up top, just rewritten. The smallest x could be, in order to make any sense, would be 0, and then the biggest it could be is 106. Right? All right, so my interval is 0 to 106. And now we're ready to just do the calculus, right? All of that was just a setup. Now we can do the absolute maximum business. So we take the derivative, right? Do it. Take the derivative. I got v prime of x is 200. It's there in the box, right? 212 minus 4x. Set this equal to 0. It says 212 minus 4x equals 0. 4x equals 212. And dividing by 4 is 53. I did that on my calculator because I'm not good at dividing in my head. All right. So this is our only critical number, and now we plug everything in. I'm going to do v of 0, v of 106. Those are the two endpoints of the interval, and then also v of 53. And see what we get. Remember to use the original formula. That one in the box there. I did these on my calculator. So this one is 212 times 0 minus 2 times 0 squared. That's 0. This one, when I plug it in, I also got 0. Remember, this is when you make the x as long as possible, which makes the y 0, and so you get no volume that way. And then volume, when the x is 53, the volume ends up being this number, 5618. This is apparently the maximum, right? And we are basically done. Let's just sort of write out what the answer is, what the question was. First of all, the question was, what is the biggest volume box? And furthermore, what dimensions make that biggest volume? So the maximum possible volume is, which number is that? The maximum possible volume. The choices are, is it the 53 or the 5618? I believe it's the 5618. This v of 53 means the volume when x is 53 equals this, 5618. And we might as well say units of this. All the units of lengths were inches, because I said they add up to 108 inches. So the units of this volume would be cubic inches. And I really have no idea how big that is. 5,600 cubic inches. All right? You could convert it to cubic feet, I guess, and I would still not have a really good idea how big that is. And then, what else did I ask? The other question was, which dimensions will give you that volume? All right, so this, to answer that question, I will say this volume happens when the dimensions are, well, it's 2, the height is going to be 2 by x by y, right? And apparently the x was 53, which gives you this value. By y, what's the y when the x is 53? Well, you remember this right here. The x plus the y has to add up to 106. So if the x is 53, the y is also 53. So the answer is 2 by 53 by 53 inches. Units. All right? So apparently the biggest volume is achieved when you just make a giant square and then have that little height to it. All right? This is like if you want to send a pizza or something. A big square with a not very tall box. All right. Like I said, I had one more example to do and then one for you all to try. We got 5 minutes. Maybe we'll just leave it to next time. Is that all right with everybody? I went a couple minutes over last time. All right, that'll do it. I will stay around for our remaining 6 minutes. If anybody has homework questions, homework's due tonight. I hope you have checked it out.